So as we're talking about these, radian mode whenever we're going to be graphing one of our trig functions. So that's one thing. We won't need that for a little while though. But what I want to try to explain a little bit is this expression you see here in the darkened in box. Looks complex, looks crazy, but like everything else that we've done with graphing, it has some similarities to some things that we've done. The only two things we're going to touch on today though are these a and b variables. We'll talk about c and d in the days to come, but that a value stands for the amplitude. And if we want to talk maybe in a little bit more of a common type sense, it's a way of describing the height of your graph. Typically, any sort of a trig graph is going to have an amplitude of 1. It goes up to 1, down to 1, and goes back and forth. But sometimes, depending on that value in front of my trig function, it can be a lot steeper, a lot skinnier. It depends. And the other value we're going to take a look at today, the b value, stands for the period of the graph. Sometimes that also can be called the cycle length. And what that means is wherever your graph starts, how long does it take for the graph to get back to that same place before it starts the pattern again? Period is typically going to be 360 degrees or 2 pi. And that's what we're going to start discussing. That's going to be the thing that might take a little time. We're going to pretend that degrees don't exist. Now, we don't just want to jump. It's not like jumping straight from English into Spanish here. We're going to have some changeover, but all of our graphs are going to be spoken in radian, okay? And all of our measurements and everything else, we're not going to see degrees for a while, except for making a quick conversion. So, I thought a good way to get introduced to this before we just jump into graphs right away would be to label a few points, but get used to this whole idea of the radians. So you see we've got 0, we got pi, we got 2 pi. So, we have a whole cycle here. Here's what I have to watch out for though. At least on these first couple of graphs, I want to know what all these other little tick marks stand for because I don't know what that goes with. So here's how you do this. If you're given a graph and this is all you're given, you're not given the other information, we're going to forget about this part for just a minute. And I notice there's 1, 2, 3, 4, 5. Okay, this is divided into 6 pieces. So let's think about this for a second. What did pi equal before as far as degrees went? As far as, if it's regular pi, yes, 180, okay, 180 degrees. So here, we know that pi is 180 degrees, okay. We also know in this case, it's divided into 1, 2, 3, 4, 5, 6 parts, okay. So in this case, it's 30 degrees per tick mark. Now here's what that means to us. It doesn't mean that we're going to go down here and write 30, 60, 90, 120. We don't want to do that, even though these will be the same values. What we're going to do, and at least you can see me do this on mine, because I don't think I'd write both of them on yours, but we could. We're going to write the radian equivalents of these degree measures on those tick lines. Now, so for instance, okay, it's going to be pi to do with something on all of these. So if you take pi, which we just said is 180, and divide it by 6, you get 30, right? So that first tick mark's going to be pi over 6, because 180 divided by 6 is 30. Or if I want to play with a calculator, which I could, here's the other thing I can do. I can say, okay, so 180, the next one's 60, okay, divided by 63, which is pi over 3. I can reduce it down this way. And I'm going to show you a couple of ways that you can do this. But I always can take that measure. Okay, I got pi over 2. Now then it starts getting a little more interesting. Now I'm going to switch up on you here for a second. And I probably should have been doing it this way to begin with. This would have been a little bit smarter of a way to go. Oops, not 190 though. Now here's one thing I don't want to do. I don't want a decimal. If I do math enter, that 2 over 3 means it'd be 2 pi over 3 would go here. And I could have done that even back with these. So like if I'd have done that back with the 30, probably would have been smarter to do it that way to begin with. Okay, I'd have gotten the 1/6, so it was pi over 6. The pi is always going to go up top, up in my numerator. And so if I just reduce the fractional part of it, knowing that the pi is going to go on top, so I've got 5 pi over 6. But I did want to show you one other place that this comes from, because sometimes people like doing it with the fractional part and just simplifying it on the calculator and saying, okay, I get this. Sometimes people are like, well, wait a minute. What this actually does when I'm trying to reduce it is I start with 1 pi over 6, and then I just keep adding 1 each time. So this next one is 2 pi over 6, but 2 divided by 6 is a third. And then it's 3 pi over 6, but 3 over 6 is a half. And 4 pi over 6. 4 over 6 is 2/3. And the reason you may want to think about it that way as well is when you get to pi, 180, you're like, well, that's 6 pi over 6. Well, 6 is canceled, it's just pi. Well, duh, right. But when I start on this other side, I can just keep counting that way. I can either do 7 pi over 6, and since 7 over 6 doesn't reduce, I can use that. Or my other option would be to say, okay, another 30 degrees would be 210. I'd do 210 divided by 180, and then do math enter, and there's my 7 over 6. You have options. And I always like to give you options, and I'll have a group of you that'll like it one way and a group of you that'll like it the other. But if you want to think of it as far as degree measures go and do that all the way through, you can, especially on this sheet here. If you want to write the degrees below, you can. But then you would just take that and keep dividing by the 180 and reducing the fraction down. So this would be 4 pi over 3. Or you could just keep adding a pi over 6 each time and keep reducing the fraction. They both work. And that's the part I want to keep stressing with this. So no matter which way you get there, and you can even double check answers pretty quick, because 3 times 180 is 540, divided by 2 is 270. That's where it comes from. And you can just keep 8 over 6, 4/3, 9 over 6, 3/2. Doesn't matter which way I tackle it. Now, I will warn you, and you're like, okay, so why are you exactly having us do all of this? Because you're not, every single time you get one of these, going to have 6 tick marks there. It may be 4, it may be 3, it may be 2, I don't know. But I have to be ready for any of those things that come at me. And that's going to be the big thing with this. Because what I'm going to do is, I'm going to get you to a point that if we get some of the basics down, you probably won't even need a calculator to do this, because we're going to talk about some base functions and things like that. But understanding how to get from degrees into a radian measure with that same thing is something that's really going to be important. So again, whether you do it with the degrees divided by 180 and then simplify it, or you just keep adding 1 each time until you get to the end and then reduce it, I don't care. I'm flexible as far as that goes. But you need to be able to do that. You can't just come up to me in 3 or 4 days and go, I don't know how to get 240 into radians. Well, we got to work on this a little. And then it's going to be the exact same going with the negatives. But I'm not going to have you fill in every single negative here. I'm just going to have you go to here, because we've got 1 tick mark there. So over here, oops. So I've got pi over 6, pi over 3. But we do have to reduce the fractions down as far as we can each time. So once I have that labeled, and again, for a lot of you, that's going to be something you definitely want to do when you're graphing these so you get accurate graphs, is now we can go ahead and we can label these points. And it's a little different from before because we're used to this being our x-axis. This is now our theta axis. That's what this little circle with a line through it is. It's going to be like our x values. So like if I'm doing this, I go over 7 pi over 6, because that's where I line up with my tick. But then my y values are just normal numbers. 1 in this case. Or when I come over to this dot, I'm in the negatives here. I didn't make these negative. Bad me. I got negative pi over 6, negative 1, negative 2, negative 3, negative 4, and label my point. And then my last one, we're at negative 5 pi over 6, and at 3 for our y value. So it's just kind of getting used to these x values all of a sudden becoming things that are in radian mode. We okay so far? Because the first one's kind of the basics. The second one, we're going to just tweak a couple of little things. And we're going to get more practice with this. They're like so far not too terribly awful. Okay. Now let's see if we can kind of put that to work here. Now, there's a couple of things I want you to take notice of. One, notice the y-axis now has changed up. We're not counting by ones anymore. You're like, ooh, that's 0. Ooh, that's 20. How many marks are there? 1, 2, 3, 4, 5. So if you take that number and divide it by 5, it means each tick mark's going to be worth 4. So I'd probably go ahead, get those labeled in. I'll even get my negatives labeled in on this one. And I can always figure that out that way. Just start counting and just count how many it takes to get to that number and divide by the number of lines you went past. But this time, notice I don't have 6 tick marks in between my pi. 1, 2, 3, 4. Right, so we're going to do 180 divided by 4, which means each of these are going to be in 45-degree increments. So again, whether you decide to write this down, that you're either going to say, okay, I'm just going to take pi and I divided it into 4, and I'm just going to add 1 to it each time, which is an absolutely fair way to do it, and then reduce them. So like if I was doing it that way with this first one, my first one would be pi over 4. 2 over 4 reduces to a half. So pi over 2. 3/4 doesn't reduce. And then I have pi. Okay, again, that's one way to go. My other option, like we did before, would just be to start doing, okay, so 45, if I looked at it in the degree mode, I'd do 45 over 180, it's 1 over 4, so it'd be 1 pi over 4. And I would just go through with each of my degree measures, 1 over 2, so it's pi over 2. And just do that for each one. 3 pi over 4, okay? And keep running it that way. And again, I want to do it all the way to 2 pi though. So if we're going to go that route, I can do it in degrees, or I can just keep adding a pi over 4 until I get to the end. They both work. So if I have half of you wanting to do it one way and half of you wanting to do it the other, it's okay, because you're both going to get to the right answer. Whether I keep going like this and saying, okay, 225 divided by 180, math, enter, it's 5 over 4, okay. Or if I just kept adding 1 and reducing the fraction. If I looked at this, it was like 6 pi over 4. Okay, I'll just reduce 6 over 4. 3 over 2. And let me see where that's coming from. But that shows you the flexibility of this. It doesn't matter how many tick marks are there. 5, 4, 3, 6, whatever it happens to be. That's how I can go ahead and get to my radian values of these. Now, while I'm adding in the ones on the negative side, if you're still kind of a little cloudy, you're like, okay, wait a minute, what did you do again? Tell me. I want to go back through and fix it and make it work easier for you. Because if you don't understand where some of this is coming from, it's going to be awfully difficult to graph it, even if you've got a calculator trying to tell you everything. So that's the one thing I want to be sure of. So any issues with how we're making our theta axis here? Like not yet. Maybe when we start drawing pictures in a minute. Okay. So I look here, I go, okay. So my first point here, what would my coordinate be for this first point to the right? 7 pi over 4, negative 8. I'm with you. What about the one up top? Pi over 4, 16. So I have to pay attention to both axes because they can change values just like that. And I'm like, ooh. And then what about that last one to the left? Negative 3 pi over 4, negative 12. Okay, so if we're just looking for coordinates, we just got to make sure our axes are labeled well, and we should be okay and in good shape there. All right, we're going to skip the back page of this first sheet. Over the next few days, we're going to be doing different parts in this packet. By the time we get done, we're basically going to have it filled in. But we're going to bounce around a little bit based on what we're doing. So we're going to skip to the actual second page where it says Example 2. And we're actually going to start drawing some stuff. So I'm just going to draw a couple reminders on here. And then we should be ready to get into the calculators. So just a reminder, when we go from 0 to 2 pi, okay, that's a full period. In other words, wherever our graph starts, by the time it gets to 2 pi, it should have completed something to be back at the same original point again. It's sort of like doing a lap of something. So here's what I want to notice on my graph right now. If I look at the big values, okay, it looks like they're broken into pieces by 90 degrees, by pi over 2. So when I go to get into my calculator, a couple of things I want to be sure of again. First thing, and I know you've done this already, but we'll put it up here again, make sure you're in radian mode, because otherwise you're going to get some funky numbers when we're doing these. Once you're sure you're in radian mode, here's the new thing you get to play with, which will hopefully be situated on your calculators already. Since my big lines are in pi over 2, that's what I'm going to do with my table. So here's how this is going to work. If you hit second and window, that's going to get you to the table set menu. So second and window gets you to here. Now, yours might be in a decimal like this, right, man? It might be somewhere else. It should be at table start 0. But then my table, since I want it to be these, I'm going to literally type in second and then my caret button to get pi divided by 2. So like if I'd have been broken up into pi over 4s like we were on the front, that's what I'd type in for my table here. So here, we're going to have that as pi over 2 on this one. And that's just to have it. There's a reminder for you if you're looking at this later going, now where did I get this from? And I could do it pi over 2, pi over 4, whatever. Now here's the one unfortunate thing. When I go to look at the chart of this, it's not going to keep it in pi. It's going to have it in decimal form. So we'll talk about that in a second. But for right now, I just want you to look at the graph of it. Make sure your calculators are working here. So we're going to go to y equals, like we have been for most graph things all along. And we're going to type this in. But instead of using theta, I'm just going to use x because I don't want to get into all the funny business of hitting multiple buttons here. So I'm going to graph the sine of x. I'm going to hit graph. I'm going to get this funky little squiggly line going up and down, up and down, up and down, kind of like a snake here. That is your base sine curve. So for us to graph it, we need to get some accurate values. So if I get my table, my second graph, I can start getting some of my values. So I see 0, 0. Now the rest of these may not be familiar to you yet. Just sine of x. So when you get here, you may not recognize some of the decimals that you see. So I just wanted to jot those down for you. You know 3.14 is pi. Y'all told me that earlier. So I understand what's going on here. But maybe with the 1.57 or 4.71, you're kind of like, is this right? Yeah, 1.57 is just a fancy way of saying pi over 2. 4.71 is just a fancy way of saying 3 pi over 2. So you may need to kind of have something to the side and give yourself a little reminder of these things. But then as I'm graphing them, so that says pi over 2 is going to be at 1. And I think, yep, for our purposes, 1 is way up here at the top. Okay. Then pi is back to 0. 3 pi over 2, which I will move the calculator here, try and keep all this stuff in a nice place, is at negative 1. And then 2 pi, or the 6.28 number, is back to 0. And again, we're trying to make curves here. We don't really want to just play dot to dot and have all these things that look rectangular. That's an entire period of the sine curve. Because notice I started at 0, and I know I went through it, but I went all the way down to the bottom, and then I end up back here. And for us to see how that period works, we also will be able to notice if we go backwards into the negative values. So there's negative pi over 2. We're at negative 1. At negative pi, we're back to 0. So see, it's just like graphing points. It's just getting used to this radian thing. All the way up to 1. Swing this back over. Negative 2 pi is back to 0. So it's just this never-ending curve that just keeps 0 to 1 to 0 to negative 1 to 0, and it just keeps going and going and going and going this way. So this is where we get to also review a little bit of what the different parts mean and what's going to happen with them. So like for instance here, when you get towards the bottom, once you've got your picture drawn, okay, it starts asking about the amplitude. Now again, we talked about on the first page, okay, the amplitude is your A value. If there is a number in front of your trig function, and we're only going to be dealing with sine and cosine, if there's a number in front, that's where your amplitude would be. If you don't see a number there, it's always 1. Just like if it were a variable or anything else, we just assume the 1 is going to be there. So, for instance, here you notice it goes up to 1, negative 1, 1. If this amplitude changed to 2 or 3, we'd go up to 2, down to negative 2, and so on. So that changes how high or how tall my graph gets. The period is my B value. That B value would show up right between sine and where that theta is at. So like if you had sine of 2 theta, okay? Normally, the period is going to be 2 pi. But if there's a number there, we divide it by that period number. So like if there was a 3 here after the sine, then we'd have to take this and we'd have to divide it by 3, and that would shrink my period up, and it'd make my squiggle really skinny, or it can make it really thick sometimes. But that's something we're going to play with. Just kind of getting you a little bit of intro work here right now. And then these last two we're not going to deal with today, but it's something you should have some familiarity with. Horizontal displacement. Sounds like you broke a bone or something. Phase shift. In other words, this is going to be my right and left shift. And that should look kind of familiar, and I'll put it back up in a minute. Remember any other things where we had shifts on the inside? Oh yeah, when we were doing parabolas, when we were doing square root functions, whatever was in the parentheses was my left or right shift. That's what's going on here. And we'll get to those, probably not till tomorrow though. So whatever in the parentheses will be a right or a left shift. And then my vertical, my up or down shift, is going to be my D value, because I forgot to write C up here. I got so excited about talking about the similarities. And just like we had before, the number hanging out on the end is my up or down. Oh yeah, that's normal. We've done that with logarithms, square roots, parabolas, and now we're just going to do it with these as well. But this base graph that you have here is basically going to give you everything that you're going to need to be able to do these. And then there's just a couple of weird things. State the theta intercepts. It's just like an x-intercept, except now, of course, using radians, we're going to use theta. So anytime that graph crosses my x, my theta axis, I'm going to have a theta intercept. Sometimes you'll have a lot of them. If it really gets squished up, you may have a ton of them. If it gets really spread out, you may have very few. But that's what I'm looking for when we talk about those intercepts. Y-intercept, still the same thing. Where's the graph cross the y-axis at? 0, in this case, right there. So no big deal with that. And then domain and range are still going to be the same. The domain is going to be my theta values, and the range is still going to be my y values. Well, since this graph from left to right goes forever and ever, it depends on what you're looking at. Now, for our purposes, since this could go forever and ever, we'd say negative infinity to infinity. They may give me a specific domain sometime. They may say just from negative 2 pi to 2 pi, like this one is. But otherwise, it would be that. And my range is going to go hand in hand with my amplitude. My lowest y value is negative 1. My highest y value is positive 1. But if I multiply by some other number, that's going to affect my range.
How do you get the A value and B value?
The A and B values are just going to be, it's tricky on this first one because we don't have any numbers in front. But when I'm coming down here, actually I'll bring this one at the top up. Like let's say, for instance, I put a number in front here. Like this said y equals 3 times the sine of theta. That would change my A value. That would change my amplitude. And we're going to do a couple of those here in a minute after we do the sine and cosine, the base graphs. If there was a number in here, for instance, between the sine and the theta, like sine 2 theta, that's where my B value would be coming from. But we haven't done anything with those yet. These are just base graphs right now. But before we're done today, we'll have messed with those to make that make a little more sense. Because there's a lot of stuff that goes on with these, especially since we're doing it in radians. But this right now, though, your base sine graph, if you just can kind of remember this part, 0, 1, 0, negative 1, 0 with that pi, everything else just shifts off of it. You won't even need a calculator. It'll be kind of cool. There's a slight difference in the cosine graph. I want to see if we can see that here. Oh yeah, we're doing good on time actually. So let's flip over. We're just going to do some base stuff today. We're going to keep life really simple. All right, we're going to do the exact same thing over here, except now we're going to be doing it with cosine. So the only thing I have to change with the calculator is going back to y equals, and now I want to do the cosine of x instead of the sine. Everything else stays the same, because you'll notice my main lines still are going by pi over 2, or 90 degrees. So I'll look at the graph. Still looks like a curve. Doesn't look a whole lot different at first look. But then I bring my chart up. Get myself back to positive here. So I make that first point and I say, okay, I see one difference already. Sine started at 0. Cosine is starting at 1. That's a big deal. But then as I move down, again, that's pi over 2. Okay, that's at 0. Pi has got me at negative 1. And remember, when you get to 3 pi over 2, that e is the same thing as 0 being there because it's just a rounding issue that the calculator does. So this is really 3 pi over 2, 0. Okay, don't think it's some big, huge number like 13 or something, because that wouldn't be right. And then 2 pi gets me back to 1. And it works the same way when I go into the negatives. Negative pi over 2 is at 0. See, that curve is never going to change. So if you're ever graphing one of these and all of a sudden it like goes weird compared to what your other ones have been, check something to make sure that you didn't somehow. And we're going to get a really fancy W type shape here. Again, we're trying to be curvy. So my cosine, when I look at it over this, does look different from what my sine curve did. But the big thing I always try to remember is, if I can remember that sine starts at 0 and cosine starts at 1, it makes remembering your parent graph or your base graph a lot easier. Everything else below is going to be the same, except, let me scooch this down just a bit. Amplitude would be the same for the base, the period would be the same for the base, and so the shifts. But my theta intercepts are going to be different when I'm working with cosine, because they're all over 90 degrees from what the sine ones would be.
Why don't you use -2 pi?
Because if we're just looking for the intercepts, we're just looking for where it's crossing the theta axis at. So just those 4. Whereas when we were doing it for sine, we actually were crossing over the axis at the -2 pi and at the 2 pi. And also, the only other thing that's going to be different on this one is my y-intercept, because now it doesn't go through at 0, 0, it goes through at 0, 1. But the domain and range would still be the same. Negative infinity to infinity, and -1 to 1, because again, my amplitude didn't change at all. It didn't mess with anything that was going to make this too incredibly difficult. So I'm just going to leave you with one last thing here today. Like I said, we're really going to take our time with this. We're going to focus in on the A value for these last 2 examples. And then I'll let you do a few problems on the worksheet, and then tomorrow we'll tackle B and C. So here's how we're going to work this. We're going to flip over here, and we're going to look at these first 2 functions. It says graph the function over the domain 0 to 2 pi. So they're telling us where we're going to look, just in this area. And they gave us the base graph just to give us something to work with, which is really cool on this. Because when I start looking at it, I go, okay, we're going to do it in the calculator, and then I'm going to show you how the shift would work without using the calculator, just to let you see you don't have to have a fancy calculator to make this work. So let's type it into the calculator, though. Let's see how this works. So we'll get back to y equals. And we're just going to type in what we see, except we're going to, again, we're going to replace the theta with an x. So 3 sine x. And we're going to graph it, and we're going to see what happens. Looks like my squiggle got taller. It's not quite so hugging the x-axis. And here's the reason why. Here, my A value, my amplitude, is 3. Well, what does that mean? Well, what that means is you're going to multiply the y value of the base by 3. Now, right now I have a chart, so I'm going to go ahead and use the chart. So I'm like, okay, so 0, 0. Then there's pi over 2. That's at 3. And then we said the e thing, okay, that's 0 again. 3 pi over 2 is at -3. And then 2 pi is back to 0. Okay. Before I connect the dots, I just want to point out something. My original point here at 0 was 0. 0 times 3 is still 0. It didn't move. Okay. At pi over 2, my base graph that we did when we did this originally was at 1. If you looked back at the very first example we drew, it would be at 1. But if you multiply that 1 by 3, that's where this is coming from. Okay? I'm just stretching it by 3. If you multiply 0 by 3, it doesn't move. If I multiply negative 1 by 3, negative 1 times 3 is negative 3. That's why this moved down here. And why my graph now takes on much more of a curve than the base graph does. But as you can see, if I just have the base graph, I could have just done the multiplying in my head. I really didn't need this. And I'm going to try that on this next one. Here's my cosine. Go ahead and get things labeled. I was bad about that on this one. I'm going to be better about it on this one. You're like, wait a minute, how'd you get those? Okay, remember, how many pieces do we have? I have 4. Well, I know pi is in the middle of 0 and 2 pi. That'd be kind of silly if it wasn't. And then I'd be like, well, I could take the 2 pi and divide it into 4 pieces if I wanted to. You'd be like, yeah, I could. Or, let's see, between 0 and pi, what's between 0 and 180? Oh, I'm frightened. What's in the middle of 0 and 180? 90, okay. Which would just be pi over 2. And again, whether you did 90 divided by 180 in math enter, or if you just said, oh yeah, I kind of see how that's going to be. This would be 270 if we're dividing it into pieces, which would be 3 pi over 2. That's where I'm coming up with this. Because again, I had 4 pieces, and they went out to 2 pi, which is 360 degrees. That's where I got these from. 360 divided by 4 means each piece is worth 90. So once I have that set, now here's how I'm going to do it. With my new one, any of them that are going through 0 are going to stay at 0, because 0 times anything is going to be 0. I see the number in front of cosine's negative 2. So we're going to multiply the y value of my base, which is already drawn in here for me. But even if you did that on your own and drew it in dotted and then put in the real one, it's not a bad idea. By negative 2. Okay. So right here, for instance, my y value is 1. What's 1 times negative 2? Negative 2. Right here in my base, my y value is negative 1. Negative 1 times negative 2 is positive 2. Right here, my y value is 1. 1 times negative 2 is negative 2. Almost looks like it's symmetrical. Now, if I had a calculator and wanted to double check something, I could. I could go to the calculator, which is one of the reasons we're going to take so many days on this, because I want you to have an opportunity to play a little bit too. But even if you have, some of you have those calculators for phones that have basic trig stuff in, if it's got a graphing function, it'll do this. Or if you've got the one downloaded for at home, and you get your graph and you look. But then let's look at the chart, because I want to see if I'm right. X value is 0, y value is negative 2. So far, so good. Pi over 2 should be 0, yes. Pi should be 2, yes. 3 over 2 is 0, yes. Negative 2. Good deal. So here's what I want you to tackle, because like I said, we're going to take these things in pieces. We're not going to go crazy. Right now, we should be at a comfort level where the first page of the worksheet should be okay. 3 problems. If you don't have a graphing calculator, doesn't mean you can't do it. you just sketch your base graph on here, which you have in your note packet, and then just multiply the y values by 1/2 or 4 or 2 and sketch that in. If you want to like take a pencil and sketch in the base graph and use a color or a pen to draw the real one in, I think it's cool. It'll make it click a little bit better for you. But have those ready to go because we're going to work on the B and C values tomorrow, and then we'll probably get to D on Wednesday.